Okay, so we have just started looking into how should an op-amp look like from all the discussions that we had throughout the semester. So we learned about single-ended and differential amplifiers, and we are kind of starting to having an intuitive sense of how the internal structure of an op-amp looks like. So in the last lecture, we saw that the op-amp can be built with, for example, the first stage being a differential amplifier with a current metered load. The second stage could be, let's say, a common source amplifier, and why the second stage becomes a single-ended amplifier as compared to a differential one. Because the first stage, which is a differential amplifier with current metered load, that converts the differential input into a single-ended output already. But the problem is that the gain is low, so that's why you want the second gain stage, so that the overall gain is multiplication of the two stages. The other thing is that the output impedance of the first stage is RO2 in parallel with RO4. Again, something that we discussed in the previous lecture and proved why is that. Now, what that means is because RO, or the intrinsic output impedance of the transistor, are generally higher, the output impedance of the first stage is high. Similarly, the output impedance of the second stage is also high. However, if you put a source follower or a common drain stage after the first two stages, you'll have an R out of 1 upon GM, because the source follower, again, something that we looked into in detail in the last lecture, that the source follower has an output impedance of 1 upon GM, because you're directly looking into the source of a transistor at the output of a source follower. However, the gain of the source follower is almost equal to 1. So you can get a high gain and a very low output impedance. Of course, the input impedance is very high because Vin1 and Vin2 are going into gates of a transistor. So that kind of fulfills all the definitions of an ideal op-amp, right? So if I go back a little bit, the ideal op-amp properties: infinite input impedance, yes, we are having that. Infinite gain, we can say that it's tending toward infinite gain, and you can plug in more and more number of stages to increase the gain if you want to. It's also having a low output impedance, and not zero output impedance, but you can have a low output impedance if you have a source follower at the final stage, because source follower looks like this, that, yeah, you have a biasing, let's say, current source on top, and you have a resistor connected at the source, your output is taken at the source, and your input is at the gate. That's how the source follower looks like. Of course, at the output node, then you see the output impedance looking into the source, and in parallel with whatever resistance is connected here on the downward direction. And because 1 upon GM is generally much smaller than whatever RS physical resistance is connected at the source, we say that the output impedance looking into this terminal is almost equal to 1 upon GM. That's the reason why we say that if GM is pretty high, you can consider R out to be almost equal to 0. So all of that is satisfied. But still, we are saying that this is not an op-amp. The reason behind that is the fact that we have too many poles in the system. We have a pole at the input, we have a pole at the first stage output, we have second stage output at the source follower output, and so on. And in the last lecture, again, we saw why those poles exist. That's because there's always resistance of the wires. There's always resistance looking at the output of any of these stages. And there is always parasitic capacitances in these wires as well as at the input of the next stage, and so on. So at every stage, you have these RC resistances. Even at the input, you have some wire resistance and capacitance. Even at the output, you have some wire resistance and capacitance. So that means you have just too many poles. However, we saw that the op-amp needs to be a single pole system. This is what we analyzed during our homework 2 and homework 3, that the open loop response of an op-amp is A0, that is the gain at 0 frequency, divided by 1 plus J times F over bandwidth in open loop. So if your open loop bandwidth is over here, let's say your gain, the open loop gain or low frequency open loop gain is this fixed quantity over here. And then after the bandwidth or after the first pole, the frequency response falls by 20 dB per decade or minus 20 dB per decade, which means that if frequency increases by 10 times, the amplitude reduces by 10 times. And that is only true for a first order system where you have only one pole. And what does the poles look like in the equation? Basically, 1 over S plus A, right? S is equal to j omega or jf as it is represented over here, that you want your op-amp to be a single pole system, that is a single S term or a single j omega or a jf term in the denominator. If you have something that looks like S plus A and S plus B in the denominator, that means you have two poles, one at S equal to minus A and the another one is at S equal to minus B, right? Because both of those will make the denominator to be equal to 0, which means that it will be a pole. Now, I have also uploaded a document which talks about poles and zeros. So if you go to your canvas, the document that has been uploaded over here, as well as for today's lecture, the poles, zeros, and Bode plots. This is something I believe you already know from your previous classes, that what does a zero mean or what does a pole mean for a transfer function of a system. So I'll not go into the definitions of that. But if you want a recap, this poles, zeros, the definition of poles, zeros, S-domain analysis, this document is published over here. And you know that for a generalized transfer function that looks like this, these are all the locations of the zeros, S equal to Z1, Z2 up to Zn, whereas location of poles are over here, which is in the denominator. Now, going back to the op-amp equation, you'll see that you want only one term in the denominator, which is dependent on S. So this is something like that. Of course, you don't want your numerator to be dependent on S, because what that will mean is that you will have a 0 at S equal to 0 if you had something like this, which is again against how an op-amp transfer function looks like. An op-amp if there is a 0 at S equal to 0, so from S equal to 0 onwards, you'll see a upward going slope, which does not happen for an op-amp, right? For an op-amp, this is frequency versus amplitude. For an op-amp, the frequency versus amplitude looks something like this, that it is flat up to a certain frequency, and then it drops at minus 20 dB per decade after that first pole. If you had two poles, it will be minus 40 dB per decade, three poles, minus 60 dB per decade, and so on. Which means that this 0 at frequency S equal to 0, that does not exist for an op-amp. So for an op-amp, the numerator is a constant quantity. At the denominator, you have this whatever S plus omega naught term that you have according to the location of your pole. All right. So now this is the equation that we have seen earlier when we are solving homework number 3, that your open loop op-amps gain can be represented as A0 divided by 1 plus JF over F open loop, where F open loop is the bandwidth of your open loop system. If you create a closed loop system, so this top one is just the open loop, that you do not have any loop around the op-amp. It's just the op-amp that you have bought from the market. That's it. Now you create a circuit, create a loop around it. Most likely that's going to be a negative feedback loop because you want your system to be stable. A positive feedback will make the system more unstable. So if you have a closed loop system, again, something that we had seen before, that for a closed loop system, the bandwidth can be extended at the cost of gain. So your gain reduces and your bandwidth extends by a factor of 1 plus A beta. Again, if you go back to the lectures on feedback earlier this semester, you'll know that this is the feedback factor by which the gain reduces and the bandwidth increases at the same time. Right? And we had represent our closed loop response as A infinity divided by 1 plus 1 over T, which is again same as, you know that A infinity for this system would be equal to 1 over beta, and T is equal to A open loop times beta, where beta is the feedback factor. You can write all of that as 1 over beta divided by 1 plus JF over FOL divided by A naught times beta. So I'm just expanding this AOL. So the gain open loop as a function of frequency, that's what I'm replacing over here for AOL, and that's how I get this term. Now, if we expand this, let me clear all of that. So if we expand this term, you'll get 1 plus 1 over A naught beta in the denominator plus JF times FOL divided by A naught beta, again in the denominator. This term over here is very close to 0 because A naught times beta, that's the loop gain, that is T. Again, you have solved your homework 2, homework 3. You know that T is a large number. In most of your problem, T was what, 70 or 100, around that range, right? So T is a large number, which means 1 upon T is a very small number, which you can approximate as 0. So in that case, if you get rid of this term, this becomes 1 over beta divided by 1 plus JF times A naught times beta times FOL. Now, 1 over beta is, of course, your A infinity. And 1 plus JF over FCL. So what is FCL? FCL is the closed loop bandwidth. Right? So we started with FOL, which is the open loop bandwidth. F subscript CL is the closed loop bandwidth. And how much is the closed loop bandwidth? The closed loop bandwidth is almost equal to A naught times beta times FOL, just from this term, right? So I'm representing that as my FCL. And again, this is something you have seen in your homework number 3, that your closed loop bandwidth is almost A naught beta times, or if you want to be exact, 1 plus A naught beta times FOL. Where is that one term coming from? Because we had ignored this quantity to be equal to 0. That's why there is a small discrepancy you might find that, why am I not taking, I just said that the feedback factor is 1 plus A beta. Your gain reduces by this factor, your bandwidth increases by this factor. But the calculations that we did here, it seems like your bandwidth increases by a factor of A naught times beta. Now, of course, A naught times beta, which is a large number, say equal to 99, 99 plus 1, which is 100, which is almost the same number, right? So 1 plus A beta is the exact quantity by which your bandwidth increases and your gain drops for a closed loop system. But you can also approximate it as just A times beta, as again, some of you have done in your homework 3, as well as I think during the first exam. Okay. So why we are discussing all of that? That is because I just wanted to have this prerequisite that, for a system, your A naught times FOL or A open loop times FOL will be equal to A closed loop times FCL. The gain bandwidth product of an op-amp should remain constant. But that is only true if the op-amp is a first order system, if the op-amp has only one pole, right? If I had 2 poles, so instead of a minus 20 dB per decade, if I have a minus 40 dB per decade kind of slope, if I had that, then the increase in bandwidth, so for example, in the previous case, because it was a minus 20 dB per decade slope, if you increase your frequency by 10 times after the bandwidth or after the location of the pole, your amplitude will reduce by 10 times. There was a direct relation between your frequency and your amplitude. And because of that direct relation, the gain times bandwidth before the location of the pole will be same as the gain times the frequency after the location of the pole. Only if it is a first order system, because first order system looks like this, 1 divided by, or let's say A divided by S plus P. Right? Where P is the location of your pole. So for that first order system, if you're, which is basically same as this, right? So if you divide your numerator and denominator with P, you'll get this 1 plus JF over FOL, this kind of a term. So only for a first order system, it is true that your frequency increases by 10 times and your gain reduces by 10 times. And only if that happens, the gain bandwidth product of the op-amp remains constant. And only if that happens, the open loop gain multiplied with the bandwidth becomes same as the closed loop gain multiplied with the bandwidth in closed loop. Otherwise, it does not happen if the op-amp is not a first order system. Right? Because if the op-amp is not a first order system, your closed loop gain will be having a closed loop bandwidth somewhere over here. And that gain bandwidth product will not be same as the open loop gain bandwidth product that you had. So this is one very important property of an op-amp, that you want your gain bandwidth product to be equal so that you can design these different types of closed loop systems and have a very simple relationship between your gain and bandwidth. Right? There is a direct trade-off that gain increases, bandwidth reduces, gain reduces, bandwidth increases, and so on. If you do not have a first order system, all of that simplicity goes away. So for an op-amp design, if you had multiple poles, if you had multiple poles, let's say P1 over here, P2 here, and P3 here, and your system looks like some part of is having a minus 20 dB per decade slope, which is between P1 and P2, and then you have minus 40, and then you have minus 60. Before you encounter the gain crossover frequency, so this frequency at which your gain crosses the point where gain is equal to 1 or equal to 0 dB, that point is called the gain crossover frequency. At whatever frequency it crosses, your gain equal to 1 line. Now, if you had a first order system, that is, if I extend this, let me draw it with a different color. So if I extend the portion that was right after my first pole, whatever gain crossover frequency I'll have over here, that will be same as my gain bandwidth product. Right? Because at that frequency, my gain is equal to 1. So my entire gain bandwidth product is my bandwidth. Which will again not be true if you have multiple poles in the system. So something that is done to fix such a system where you have multiple poles and you want a single pole is something called pole splitting or compensation. Again, the actual math behind pole splitting or compensation will be covered in your eCircuits 2 as well as Analog Circuits 1 classes. I'll not go through the math, but you should know that the method through which this problem can be solved is called pole splitting. What does that do? That if you had multiple poles before your gain crossover frequency, if you had multiple poles, what you want to do is that somehow you want to push these poles away. Somehow you want to push these poles towards the right-hand side, towards higher frequencies. And the trade-off that happens as you're trying to do that is that your first pole, the dominant pole or P1, that actually moves towards left. So if you see this right-hand side picture, that your dominant pole P1 has moved towards left, whereas the non-dominant poles P2 and P3 have moved towards right. And through this technique, you can achieve a single pole system at the cost of a lower bandwidth. So this is called pole splitting or compensation. Again, the math will be taken care of in your eCircuits 2 class, but the technique is called pole splitting. You can create a first order system out of a single second order or a third order system at the cost of a lower bandwidth. Because what pole splitting does is that initially your P1 was at this frequency and the non-dominant pole was here, right? What will happen after compensation or after pole splitting is that the dominant pole will shift towards left and the non-dominant pole will shift towards right. And that is the reason why this is called splitting. So the details of pole splitting will be covered here in EEE 4306, which is your eCircuits 2. Now, for now, we'll ignore that, like whatever math is there. However, we are going to use that concept in the problem that we'll be solving in terms of op-amp design. A few other concepts that I want to go through before we actually start the op-amp design. Of course, poles and zeros, you already know that this is the general form of a transfer function of a system, S plus A divided by S plus B times S plus C. So in the Bode plot, which is basically a graphical representation of the transfer function, each pole will add a minus 20 dB per decade slope and a minus 90 degree phase shift. Why do we add a minus 90 degree phase shift? Because for each pole, this is something again we had covered earlier in the classes as well. That for each pole, you know that you are going to have that minus 20 dB per decade slope, but at the same time, each pole is having a minus j term. Your S is equal to j omega. So when your S is equal to minus B, right? Or when your omega, that is the frequency, or let's say, let me write it in this way, j omega is equal to minus B. At that point, you have a pole. Now, what that means is that when your omega is equal to minus B over this complex term, now you know that minus 1 is equal to j squared from your high school math. That minus 1 is equal to that complex quantity j squared. So minus B divided by j, that becomes j times B. So at omega equal to j times B, you'll have the pole. Right? Just directly calculating from this term. So each of these terms, so and that is at the denominator. So at the denominator, you will have this j term. Having a j term in the denominator is same as having a minus j term in the numerator for any quantity, for any transfer function, right? So having a j term in the denominator is same as having a minus j term in the numerator, because you can. So what I'm saying now is that let's say I have a j in the denominator, that is same as having a minus j in the numerator. Why? Because let's say I multiply both the numerator and denominator with j. So I, let's say, do this and multiply this with j as well. So what is j times j? That's j squared, that is minus 1. What is minus j squared? That would be plus 1. So this is equal to 1 over j. So having a minus j term in the denominator is, a j term in the denominator is same as having a minus j term in the numerator. So because your poles are at the denominator, and poles will represent a frequency corresponding to jb, that is the frequency that you are corresponding to, which means that at the numerator, if you consider the effect of that term in the denominator, and you want to reflect the effect on the numerator, that is same as having a minus j term in the numerator, which is equivalent to having a minus 90-degree phase. Again, going back to some of the complex number theory that you learned in your high school. So each pole will have an additional minus 90-degree phase, and each pole will have an additional minus 20 dB per decade slope. And again, the details, the proofs and everything are provided in the document. So if you want to refresh your memory on poles and zeros, please do that. Some of the other nomenclatures and definitions, that when your gain plot, when this body plot, which is basically a representation of your gain versus your frequency or angular frequency, and also the representation of your phase versus that angular frequency. So if you have two poles, then after the second pole, you have a minus 40 dB per decade slope. And when you're crossing this gain equal to 1, which is your x-axis, and if gain is represented in dB, let's say you represent the y-axis as dB, right? So in that case, gain of 1 in linear scale will be equal to 0 dB. So I can also say that this is my 0 dB line. And when my gain crosses that 0 dB line, that frequency is called the gain crossover frequency, or GCF. Similarly, each pole will contribute to a minus 90-degree phase shift. And this is something, again, we saw when we were solving our homework number 3 in class, that at the location of your pole, you have a 45-degree phase shift. Originally, you had 0. At the exact location of the pole, you will have 45. But at infinite frequency away from the pole, you will have a minus 90-degree phase shift. So start from 0, have minus 90 degree because of the first pole. And again, because of the second pole, you have another 90 degree. So you have minus 180 degree. Right? So your phase changes by 180 degree starting from a point when you had 0 degree, because each pole adds a minus 90 degree to the phase. The point where, or the frequency at which your phase changes by 180 degree is called the phase crossover frequency, or PCF. So just like the GCF or the gain crossover frequency, you have your phase crossover frequency over here. Now your phase margin is, again, a figure of merit that will be defined and will be very important for any amplifier. That phase margin is defined as the amount of phase at your gain crossover frequency plus 180 degrees. So whatever phase you have at your gain crossover frequency, which is in this case over here. So because you already reached minus 180 degree, which means that if you had another pole, over here, that would start having some effect, and your phase will be even lower than minus 180 degrees at the point where you have gain crossover frequency. So phase at your gain crossover frequency plus 180 degree, that is called a phase margin. And for a stable system, you have greater than 0 degree phase margin. For an unstable system, you have less than 0 degree phase margin, and we'll discuss why. Okay. For an unstable system, where by instability I mean oscillations, that you're trying to create an amplifier, but your amplifier starts oscillating. That can happen a lot. Specifically, when you start designing an op-amp for the first time. You may end up designing an oscillator. On the other hand, you're trying to design an oscillator, you may end up designing an amplifier if you're not taking care of the gain crossover and phase crossover frequencies properly, which means the relation of phase margin, that your phase at gain crossover frequency plus 180 degree, that needs to be a relatively positive number. And if that is positive, then you have a stable system. If that is negative, then you have an unstable system. What is the meaning of having a negative phase margin? If your gain crossover frequency happens before your phase crossover, if your gain crossover frequency, which is here, or before, so your gain crossover frequency is larger than your phase crossover frequency, right? That's what you see in this case, that your gain crossover frequency is larger, but by the time you reach your gain crossover frequency, you had already reached your phase crossover frequency. And in that case, your phase margin will be negative because you have already reached 180 degrees. So adding 180 degrees to a minus 180 or something which is even more negative than minus 180, which means that your phase margin will be negative or zero. And that will be called an unstable system. On the other hand, if your gain crossover frequency is less than your phase crossover frequency, in that case, the system will be stable. So if you had a first order system, let's say you had a first order system like this. So this would have been your gain crossover frequency, which would definitely be higher than the gain crossover frequency over here. So that moves towards right. However, because this is a single pole system, you will only add this minus 90 degree phase. You'll not get to minus 180 degree unless you have that second pole. And let's say the second pole happens only after your gain crossover happens. So only after your gain crossover happens, let's say you want that second pole, that means you're still at minus 90 here, and you'll be at minus 135 at the location of the second pole. And then at some point, you'll cross your frequency axis over here, which means that your gain crossover is happening at a lower frequency as compared to your phase crossover. If you have a single pole system, because single pole system can only have a 90 degree phase shift. You need at least a 180 degree phase shift to create a phase crossover. Before you have this 180 degree phase shift, you cannot have a phase crossover because it is defined in that way. The gain crossover happens when you cross the 0 dB gain line. The phase crossover happens when you change your phase or shift your phase by 180 degrees as compared to the original phase, which was 0 degrees, let's say. So to have a 180 degree phase shift or to have a phase crossover frequency, you need at least two poles. So a single pole system cannot have a phase crossover frequency. But a single pole system can have a gain crossover frequency because you're reducing the gain by minus 20 dB per decade. And at some point, you'll cross that 0 dB gain line. So a single pole system can have gain crossover frequency, but a single pole system can never have a phase crossover frequency. And if you can never have phase crossover frequency, your phase margin will always be positive. Right? Because if you had only one pole system, ideally, so you reach to minus 90 and you stay at minus 90 for infinite duration, if ideally you have a single pole system or a first order system. So at gain crossover frequency, you still have minus 90 degree phase. You add 180 degree to it, which means your phase margin will be plus 90 degrees. So very much into the positive realm. That means that the system will be stable. And that is another reason why you would want a first order system or a single pole system. Because as soon as you have multi-pole system, you can start oscillating. Okay, now let's understand this a little better. That why do you start oscillating if you have a negative phase margin? We saw that a multi-pole system can have a negative phase margin or a zero phase margin in the best case scenario. But a single pole system will always have a positive phase margin. So why does positive phase margin means a stable system? First of all, why do you want a stable system? Because we want to build an amplifier. We don't want our output to oscillate at whatever frequency and amplitude it wants. So we want a particular frequency and a particular amplitude. That is the whole point we are designing an amplifier. So we want a stable system, but instability means there would be oscillation. And oscillation is determined by something called Barkhausen's criteria. Again, you may have heard about this name in any of the other classes or lectures. But what it says is that there are some necessary conditions for oscillations. One necessary condition is that the phase difference in an oscillatory loop needs to be a multiple of 360 degrees. Why is that? Let's say I have a loop. I have an amplifier and I have a feedback system, and I feed back some of that signal back to my input. Now let's say I have a sine wave, a very small amplitude sine wave applied at the input side. My amplifier amplifies that signal. I feed back some of it on the input side again. And by the time I have my feedback signal available at the input side, let's say I have removed my original input. Now, if my feedback signal looks exactly same as my original input, let's say it is having a gain of 1 after feedback, when the signal comes back, I have the exact same amplitude and exact same phase as the original signal. Does my amplifier or feedback system understand that my original signal had been removed, and what we are seeing is just the feedback signal? My amplifier cannot understand that, and my feedback system cannot understand that. So even if I'm not applying any input, I can get sustained sine wave outputs, oscillations at the output. If I have such a system where after removing my original input, whatever feedback signal I have is having the exact same amplitude and exact same phase as the original signal. It's as if you first apply the signal and then remove it. By the time the original signal gets amplified and fade back at the input, you have already removed the original signal. But the system does not understand that. System has no way of knowing that the original signal had been removed, because this feedback signal that comes back looks like the exact same amplitude, looks like the exact same phase. And then it will be passed through this loop again and again, again and again, and again and again. And that's how oscillations are created. So for Barkhausen's criteria, what it says is that the phase difference in that oscillatory loop has to be a multiple of 360 degrees. What is 360 degree phase difference? If I have a sine wave and another sine wave which has a 360 degree phase difference, they will look exactly the same. Right? Now it could be a multiple of 360 degrees. 720 will also look the same. 0 degree will also look the same. 1080 will also look the same. Barkhausen's criteria talks about just that your phase difference in an oscillatory loop has to be a multiple of 360 degrees so that your feedback signal looks exactly same as your input. And gain in that oscillatory loop should be, let's say, equal to 1 or more than 1. If it is more than 1, then that oscillation will build up from a very small amplitude input signal. You can build higher and higher amplitude output signals if the gain is more than 1. But if the gain is less than 1, then in the loop, the oscillation will die down, because every time you complete the loop, your oscillation amplitude will go down if the gain is not greater than 1. So you want at least equal to 1 so that you can sustain the amplitude, or you want more than 1 so that you can build up higher and higher amount of oscillation amplitude. Questions? How do you prevent positive feedback? So the way this works, or for example, how positive and negative feedbacks are defined, as we had discussed in the class earlier, that whether it adds up to your original signal or subtracts from your original signal. In this case, you want your feedback signal to be exactly same as your original signal, right? You want the positive feedback. For an oscillator, you want the positive feedback because you want the system to be unstable. Oscillation means instability. Right? You don't want to remove positive feedback. You want positive feedback.
But ideally, we want the gain.
Equal to 1 means that you'll have the same amplitude that you had originally had over here. Now, why it is preferred to have more than 1 gain is because nobody applies a signal to an oscillator. Oscillator just starts oscillating, right? Maybe if you have come across, let's say, any oscillator systems, and you have come across many oscillator systems, like any kind of mechanical clock, let's say, is an oscillator system, and so on. Crystal oscillators are an oscillatory system. If you have a gain of exactly equal to 1, a small input amplitude, let's say noise, let's say a small input amplitude at some frequency, which is because of noise, that will stay at that same amplitude at the output as well. So if your noise was a microvolt amplitude, your output will also be microvolt if your gain is exactly equal to 1. But if your gain is more than 1, that microvolt after one cycle, it may become millivolt. After the next cycle, it may become volts. And then you'll see a large amplitude oscillation at the output, which even you want for an oscillator. That's how oscillators are built, right? So you don't want to avoid positive feedback. You want to control that positive feedback, right, for an oscillator. So one other great example in this regard is basically nuclear reactors, where you want that positive feedback to happen, right? But you want to control that positive feedback in a nuclear reactor so that you can use that energy in a beneficial way. So that's also, it's not an electrical oscillator, but it's the same concept that you want that positive feedback in a nuclear reactor. You don't want to avoid it. If you avoid it, there's no nuclear reaction. Right? How do you control the positive feedback? That's a great question. So this positive feedback, now this phase difference, the phase difference does not happen at any frequency. The phase difference that you see in an oscillatory loop is also a function of frequency. So you want to, when you say you want to control that positive feedback, that means you want to control the frequency at which this oscillator oscillates, right? So you'll design it in a way, and again, there are entire classes, entire courses just on oscillator design, right? And there are entire books just on oscillator design. So the way you want to do it for an oscillator is that the phase difference that you create in the loop, which is a multiple of 360 degrees, that will be a function of the frequency. And depending on at what frequency you want to oscillate, you will create that phase difference so that only at that frequency, the phase difference becomes a multiple of 360 degrees. That's how we can control an oscillator. Again, it might sound a little hand-waving at this point, but that's only because this course is not about oscillator design. There are courses which I can teach on oscillator design for 30 lectures. So I just want to spend maybe 10 minutes on this to introduce the concept, but you can always go deeper and deeper into oscillator design. Okay. Now, if your amplifier is a common source amplifier, you know that the common source amplifier already has a 180-degree phase difference. How does the common source amplifier look like? The common source amplifier has its input at the gate and output at the drain. And you know that there is already a 180-degree phase shift between the input and output. If your input looks like a sine wave like this, your output will look the 180-degree phase shifted sine wave. So you already have a 180-degree phase difference even at low frequencies, even at very low frequencies close to DC. Now, at some other frequency, if you get another 180-degree phase difference, right? So you already have a 180-degree phase difference because you are using a common source amplifier. If you somehow get another 180-degree phase difference, the total phase difference becomes 360-degree and the system may oscillate. Correct? And if you have two poles, that is basically one pole coming from one common source amplifier and the second pole coming from another common source amplifier. So if you just put two common source amplifiers in cascade, the first one will constitute a 180-degree phase shift. The second one will also constitute a 180-degree phase shift. And the total might become 360 degrees at any frequency that you want. So you can start oscillating at any frequency. And that's what you have to be careful about when you are cascading multiple common source amplifiers. Because each of those are 180-degree phase shift, right? And two of them makes 360 degree at any frequency that you want. However, if you have, let's say, you have a positive phase margin, right? If you have a positive phase margin, what does that mean? That if you have this positive phase margin as we have seen over here in this kind of a system, let's say. So you have a single pole system. Let's just assume we have, somehow we build a single pole system. That means there's only 90-degree phase shift. This is a 90-degree frequency dependent phase shift, right? That at some frequency I have this 90-degree phase shift. And if I do not have the second pole, I do not have the other 180 degrees. So if I do not have the second pole, I do not have the other 180 degree. Of course, you can argue that my common source amplifier itself can give me another 180 degree, right? So that's why any system can still oscillate. Even with the common source amplifiers, if you cascade it with another, the system can oscillate. What you need to do is this analysis of gain crossover and phase crossover frequencies, which can also be done using simulators. There, if you find out that your phase margin is positive, what does that mean? That at my gain crossover frequency, whatever phase I have, that is only changing from the initial phase by less than 180 degrees, right? So if you had one pole, you're changing by 90 degrees, and then at the gain crossover frequency, you still have a phase margin of positive 90 degrees. Let's say after that, you encounter the second pole. Your second pole is after your gain crossover frequency. So you'll start your minus 40 dB per decade after your second pole, and you'll start seeing that another 180 degree, another 90 degree phase shift in the phase after that point. But when you reach that 180 degree phase shift over here, at that point, your gain is already much lower than 1. Because remember that this line represents gain equal to 1 or gain equal to 0 dB. If your 180 degree phase shift happens after the gain crossover frequency, then you're covered. You're not meeting Barkhausen's criteria because your gain is already less than 1 at that point. What does Barkhausen's criteria say? That the gain has to be more than 1, at least equal to 1 or more than 1 to create the oscillation. Because if the gain is less than 1, the oscillation will die down. In the first cycle, you may have a millivolt of input signal. In the second cycle, you may have 0.1 millivolt. Third cycle, you have 0.01 millivolt. And then after 10 cycles, you have almost no signal at all. So gain has to be more than 1 for oscillations to happen. If you prevent that, oscillations do not happen. Right? And what is the easiest way to prevent that? The easiest way to prevent that is to have a high or a positive phase margin. That means that your gain crossover frequency happens at a much lower frequency than your phase crossover. And that is only possible for a first order system, that you have minus 20 dB per decade. So your phase is only changing by 90 degrees. Your phase changes by 180 degrees after the second pole. And if that second pole happens after the gain crossover, then at the gain crossover, you have a positive phase margin. Whatever this margin is, that's always positive. So a positive phase margin will determine or will indicate a stable system. Now you can do a lot of math, and that's why I said that we are not going through the math. We'll try to understand this intuitively. That why does positive phase margin mean that the chances of oscillations will not be there? That is only because when you have chance of oscillation, when do you have the chance for oscillation? Because your common source amplifier already has a 180 degree phase shift, right? If you had another 180 degree phase shift from somewhere, then you can start oscillating because your total phase shift in the loop will become 180 plus 180, that is 360. And that's what Barkhausen said, that if your total phase shift in the loop is a multiple of 360 degrees, then you oscillate. 180 comes from your common source amplifier. The rest of the 180 is this frequency dependent phase that can be there because of these poles, location of these poles. Okay. But if you have a positive phase margin, that means at the point when you have that additional 180 degree phase, your gain has already become less than 1. And if the gain has become less than 1, you cannot oscillate. Or even if you start oscillating, after a few microseconds, you'll not oscillate anymore because the amplitude will die down. So in that case, the oscillations may look like this, that you start with a large amplitude, then it dies down, and then you get a stable operating point. That can happen. That happens to many systems. And that is called the initial transient in many of these systems. So it's very important to have a positive phase margin. And to have a positive phase margin, you need to have a single pole system. That means you need to do pole splitting or compensation to make sure that you effectively have a single pole system. If we had done the math, which you guys will learn in e-circuits too, you will see that for 60-degree phase margin, the location of the second pole has to be at least 2.2 times away from the gain bandwidth product. So for 60-degree phase margin, the gain bandwidth product or the gain crossover frequency for the single pole system, because this is a single pole system, those two are the same thing. The GCF is equal to the GBW. If you want a 60-degree phase margin, P2 needs to be equal to about 2.2 times the gain bandwidth product. And we are not doing that math. That math will be taught in e-circuits too. But this number can be proved from that calculation that we'll anyway be doing later. And why do we want, let's say, about a 60-degree phase margin? We said that we want a positive phase margin. So 1-degree phase margin is also positive. And 1-degree phase margin also indicates that there should not be any kind of oscillation. So why do we not have 1-degree phase margin, and why do we want a large phase margin like 60 degrees? That is because there is always process variations, manufacturing variations in the system, right? Because of manufacturing variations or voltage variations or temperature variation, your 1-degree phase margin may not remain that positive 1 degree at all operating conditions. Maybe the transistors heat up, the transistor or the amplifier that you have bought from the market. After a little while, that amplifier heats up, and because it heats up, that phase margin will change. And maybe that phase margin will go beyond zero, below 0 degrees. So you want to have some guard band or tolerance limit so that, and that is the reason why you design it with 60-degree phase margin to start. That's generally a rule of thumb in amplifier designs. Okay, so what we learned is that for positive phase margin, we want a phase like the PCF. At PCF, your gain has to be less than 0. And in that case, it will not oscillate. Another concept that we'll use in our op-amp design is the concept of slew rate. So what slew rate says is how fast does the output move for an ideal input. Let's say I have an ideal inverter. An ideal inverter is a digital circuit. We'll also take a look at digital circuit right after Thanksgiving. So for a digital circuit, it inverts any logic level. So if you have a logic level 0 and a logic level 1, and then you switch from logic level 0 to logic level 1 at the input of the inverter, at the output of the inverter, ideally, you should directly or instantaneously switch from a logic level 1 to a logic level 0, right? Because that's the inverted version of how the input switches. However, in reality, there would be a time delay. The logic level 1 will not instantaneously go to logic level 0. There would be a time delay, T, during which the logic level changes. So if your logic level is VDD to 0, then the slew rate is defined as VDD over T, because that's the amount of change that you have in your voltage divided by the time that you need to make that change. So that is called the slew rate, and it is defined as the amount of time, the ratio of the change in voltage divided by the time required to make that change in the voltage. So this is another concept that we'll be using when you do the op-amp design. Now let's start looking into the op-amp design, and we'll finish this entire discussion on op-amp design in Friday's class. This is also going to be your homework 1. So in the last page of this discussion, your homework 8 problem is also given. Now you need to design this above op-amp. And if you look into the op-amp structure, it's basically the same structure as you see over here, that you have a differential amplifier with current mirror load. So this is the current mirror load over here, M3 and M4. They create a current mirror, right? This is the mirroring of the current happening from the left side branch to the right side branch. At the bottom side, you have this tail transistor working as a current source, and that is mirrored from the I bias that you see over here on the left side. So this is your differential amplifier with current mirrored load. And on the right side, what you see is a common source amplifier. Your input is applied at the gate of this PMOS. Now, the only difference that you see from the common source amplifier that you learned earlier in class is that this common source amplifier has a PMOS input. Instead of NMOS input, which you learned earlier in class, now you just have PMOS input, but that's the only difference. And you already know that NMOS and PMOS are just duals of each other. In terms of gain, there should not be any difference at all. It's just that you have to bias them correctly in a way that is dual to your NMOSs. So this is still a common source amplifier. Your input is at the gate and your output is provided at or output is taken from the drain. Of course, this is the second stage. You should have another third stage after this, which will talk about your source follower. So this is basically the structure we are looking at. Diff amp with current meter load, followed by a common source amplifier, followed by a source follower. Now, because you already know how to design a source follower, I'm not putting that as part of your homework. But in a real amplifier design, you will have to take care of this. So your homework is basically designing these first two stages. And we'll first look at that homework design example problem in Friday's lecture. And then hopefully we'll be able to solve that homework over the Thanksgiving break. Before the Friday's lecture, I'll ask you to maybe go through this solution once before I discuss this in the class, because there are a lot of intricate concepts. And by designing, what we mean is that design the W over L ratios of each of these transistors. This is again something that I said in the beginning of our discussion on MOSFET, that when someone asks you to design a circuit, they're asking you to find out the W over L ratios of all the transistors. So we learn how to do that for this op amp in the next lecture.